The real reason we wanted to parameterize surfaces is to be able to integrate scalar functions and later vector functions on them. I think the best place to start motivating the definition that we're about to see is to go back to one-dimensional case. In Calculus 1, the very first time you were introduced to the notion of Riemann sums and integrals, you were able to integrate real valued functions, scalar functions, defined on some interval. So this is the original definition that makes sense in terms of Riemann sums. Now in this course, you learned that if we have a one-dimensional object that is not really a line segment, and rather it's a curve in R2 or maybe even in R3, the way to integrate a function on it, that means the way to define this quantity here, integral of a scalar valued function f on the curve C, is to parameterize it, the blue stuff going on here. That means to find the map RT from an interval that when t ranges between a and b, it covers the curve and it's differentiable and it's injective, it doesn't cover any piece twice and stuff. Then we can define the integral of f along the curve C by calculating this quantity. This is a calculus 1 quantity. So in that case, we go back to our original notion of integral, and again, this integral is happening on an interval, and we have a meaning for it from calculus 1. The point of this definition is that the value is not dependent on how you parameterize, which is very, very important. If two people came with their different parameterizations and they ended up producing a different value, it would be so stupid to call it the integral of f along the curve, because depending on who parameterizes the curve and how we parameterize it, we would produce a different number each time. The point is, again, it's a theorem that this will be independent of how you parameterize, and therefore it deserves to be called the integral of f along the curve C. There are other reasons also why it deserves to be called that. For instance, if you integrate the constant function f, it gives us the length of the curve because this becomes 1, and integrating r prime t absolute value we've seen is the length of the curve. There is, though, another object we can integrate now over a curve, and that is a vector field. So if we have a vector field on some region including this curve, then we can integrate this f along the curve. That is, we can make sense of this quantity here by this definition. This time, because we have a vector, we don't take absolute value of r prime of t and rather put it in the vector form, and to get a real valued function, we dot product it. So this side, the right hand side, is again a calculus 1 integral, but one shows that this is independent of how you parameterize, so it truly is an object that depends on the curve and not how one parameterizes. Parameterization is an extrinsic, is an artificial way of describing a curve, and the real thing is the curve itself lying in the space. But parameterization helps us evaluate this quantity and even define it mathematically to begin with. I hope this analogy will now help you understand what's happening in the 2D case. So we have, again in this course, this is a huge course, you have seen so many new concepts. We have seen that if you have some domain D in the xy plane, we can make sense of this integral. So this part that was a million weeks ago in some section, so this is like defined. We know what it is, it's the Riemann sum, and also we know some tricks to calculate it and whatnot. So if you are given a scalar valued function f on a region in the plane, you can integrate. Now we want to integrate a scalar valued function not defined on a region of the plane, but on a surface that has curvature. So we have some two-dimensional object, but with some curvature sitting in R3. So y, x here, and z here. And as I have been following this convention with colors, so green is the parameterization region, blue is the surface that we are interested in, that's the real thing, the blue is the real object. But to describe it, to be able to do calculations, we look at it through the lens of something called a parameterization, a function that takes, okay, change of heart, uv here. So we call it u and v. So r of uv is a function of x, it's a function of uv, and produces a point in the space. And if we run uv on the set D, we produce the surface that we want. Okay, so definition in mathematics doesn't have to be proven. It's something we set, but we try to make to justify the definition and say why it deserves to be called that. So here we won't get into details of that, except mentioning that again this will be a quantity independent of parameterization. So I want to define what it means to integrate f along the set S. And instead of saying area, it is two-dimensional really, it has area, infinitesimal area, but to emphasize that it is a non-flat surface, possibly, we use ds instead of dA, the area. But I would have personally loved to use dA still to emphasize its area. Is by definition, so I'm not saying something is equal to something, I'm not claiming it, I'm defining it. To us, this will be the very meaning, this is the first time this object is being born. We are going to give this object the following meaning. Because we have this R parameterization, we, instead of integrating along the curved surface, which we have no idea of how to do, we transfer everything back to the region D. F is defined on the surface S. F defined on S, it's a scalar valued. And well, I have to put UV, I'm integrating over D region, so in D region I have UVs, but F doesn't know UVs, so we put UV into R, we travel to S, and now we plug that point into F, we get some real number. And then we want to do du dv, right? Du dv integral. Except that we multiply into another value, and this will be the familiar Ru cross product Rv vector, but take an absolute value. So let's see. So given scalar f on S and parameterization RUV, we define the integral to be equal to that end of the sentence. Let's check if this side, which we claim to be something meaningful, is indeed meaningful. First of all, I am integrating something over here in the D region. This is a scalar function. This is a scalar function at the end of the day. You multiply, you have a scalar value. And now you're integrating it over the region D. And this integration, we do know what it means from all the previous chapters. And that, ladies and gentlemen, is what integrating a real valued function on a surface means. And as before, the key fact, which everything is dependent on whether this is true or not, is that this quantity This requires a lot of mathematics to prove. Even linear algebra is involved here. So this quantity is independent of specific parameterization. That's why it deserves to be called an integral over the surface. Have a comparison with the previous case. You have this element here. This is the area element. Let me use green. This area element is here. Without this factor of this cross product, we wouldn't have an object that does not depend on parameterization. And in the previous case, we had this ds being equal to r prime of t dt. So here, this is called the line element, line integral element. Here you can call this the surface area element. This is the infinitesimal quantity. That means the Jacobian built into it that makes this object intrinsic, independent of the parameterization. That will be how we define the integral of a real valued function on the surface. In case so a test. If f is the constant function 1, then integral of 1 over the surface will equal integral over the parameterization domain of Ru cross Rv d u dv. And this we have seen before, that this is area of the surface. And that perfectly makes sense. If you integrate the constant function 1, you are adding up these tiny bits of surface together. Think about Riemann sum, and that should end up giving us the total surface area. Okay. Another application that the book mentions of surface integrals is application to density and center of mass. So let rho be the mass density of a piece of metal in the shape of surface S. So we are only talking about the shell. Suppose that we have built this shelter, say, in a bus stop, let's say, out of some material which is not uniform. So this piece has some density, this piece is built of some heavier thing. These are different materials patched together. So at every point there is certain density per square feet. And we want to see how much the whole thing weighs. As we have talked about this before in other scenarios, the total mass will be just integrating over this surface the density function ts. The book, when talking about a function defined on the surface, the book uses x, y, z. It gives the impression that this is a three-dimensional, three-variable function. This is only because technically a point on the surface is a point in 3D, but these functions need not be defined on everywhere, need not be defined outside the surface. They only need to be defined on the surface. That's why I don't plug in anything. So if directly you have a description in the parameterization, you can just go ahead and write FUV. So to keep this confusion out of way, I just don't plug in anything at all. And once you parameterize, you know what to plug in. Then the functions will have formulas. So integrating rho against the surface area element, this is the largest, will give us the mass. Now x bar, here we need now to look at the coordinate system. So where is the x average of this? Well, that will be 1 over m. Integrate x against rho ds. Notice that this is a scalar function. X multiplies into something over the surfaces, and similarly y bar and z bar are defined. If you want the moments, you can you just multiply into x squared and things like that. I wouldn't torture you with moments and the other stuff from physics in 3 dimensions. We have discussed them in detail in 2D. Okay, let's see how this integral formula, what this integral formula looks like in the special case when our surfaces were not parameterized like RUV with a random R, but rather within the XYZ plane. So these are one case, one example of how we have parameterizations of a surface. So in this case, it's the graph of some function. So here is z equal f of x y graph, and we look at the projection, the shadow. So if I follow my convention with my coloring, the shadow is the parameterization region, and this thing up here is the actual surface we are interested in. By the way, because I have been using integrating a function, f functions, let's give this a different name, g. So this is z equal g of xy is the surface. Now how do you integrate a function f on this surface? Well, if you follow these formulas, and we saw this in the case of surface area, we saw that RU cross RV is equal to 1 plus f of x, g of x. Now our f is g of x squared plus g of y squared. That is this. And well, here you may ask, what is r? Well, r here is r of xy equals, so xy here is doubling, as meaning you can think of one copy of xy in a separate coordinate system in 2D, and then they also represent the 3D projection in the 3D, and this will be g of xy. So this is the parameterization in the sense of having an RUV of this surface, and if you compute the partial with respect to x and partial with respect to y, cross product, take absolute value, you will end up with this. So this will be integral over the parameterization domain, which is d of f values multiplied this surface element. So that will be 1 plus gx to the power 2 plus gy to the power 2 dx dy. So in this special case, when surface is given by a function, by graph of a function g, this is how you integrate it. Okay, great. So happy integrating functions on not just parts of the plane, but on curved and bendy spaces like this one.